We're going to use a root test to determine whether this series is convergent or divergent. So we take the limit as n approaches infinity of the nth root of the absolute value of a sub n, which is 1 plus 1 over n to the n squared. So we can drop the absolute values since this is going to be positive anyway. Limit as n approaches infinity of the nth root of 1 plus 1 over n to the n squared. So this is the same thing as dividing this here. N squared divided by n, which is just n. N squared divided by n is the same thing as having subtracted 1 from 2, which is n to the power of 1, which is n. So now that we have this, we could plug in infinity. This is going to give us this, because this goes to 0. So 1 to the power of infinity is an indeterminate form, so it's not just 1. We can't just say it's 1. We have to keep going, so we could use the natural log properties. We have limit as n approaches infinity of e to the power of natural log of this. So the reason we're doing this is because now we can use a natural log property that we could bring down the exponent. We can bring down the exponent to be multiplied. Limit as n approaches infinity of e to the n natural log of 1 plus 1 over n. Now if we plug in our infinity, we would get e to the infinity times the natural log of 1 plus 0. Because we plug infinity in that denominator, that's going to give us 0. Natural log of 1 is just 0. So we get infinity times 0 in that exponent. Infinity times 0 is still indeterminate. So we have to do something else. Limit as n approaches infinity. Well, we can notice that we could divide by 1 over n, and that would be the same thing as multiplying n. So now we have it in fraction form. So we can have the natural log of 1 plus 1 over n, and then we're dividing by 1 over n. That's exactly the same thing we have there. Now we could use L'Hopital's rule and take the derivative of both the top and the bottom, because notice that if we plug infinity, we get 0 in the denominator and 0 in the numerator again, because natural log of 1 is 0. 0 over 0, indeterminate, and lets us do L'Hopital's. So this is n to the power of negative 1. We take the derivative of that. That's negative n to the power of negative 2. We take the derivative of this, and that's, if you remember, you take 1 over whatever's inside of the function, and then use the chain rule. So that's, I should probably take that step by step. So we have e, and then we have 1 over 1 plus 1 over n, like that. That's the derivative of the whole thing. And then by the chain rule, we take the derivative of what's inside. So this goes away because it's a constant. And this is n to the power of negative 1, which is the same thing as, when we take the derivative, it's the same thing as what we had in the denominator. So now we can cancel out the negative n to the power of negative 2. And we're left with this nice exponent there for e. We plug in infinity, and this goes to 0, so we're left with 1 over 1, which is just 1. So we're left with e to the power of 1, which is just e, which is greater than 1. So by the root test, it diverges because we had something which is greater than 1.